Hello everyone. Today I'm going to discuss Taylor's expansion. Actually, I want to discuss about Taylor's expansion for a function in more than one variable. But then just to give you a gist of how Taylor's expansion is done for a function in single variable, I've written this form. Like suppose if I have a function y is equal to f of x, then the Taylor's expansion for the function would be at a point x is equal to x naught would be given like this. Thales has proposed it to be like this. Now here this function has to be continuous and differentiable. And differentiable, of course, that is the condition. Okay, differentiable n minus 1 times. Okay, that means all incidentally it should be differentiable, right? About a point x is equal to x naught. This is how the Taylor's expansion looks. There's a rhythm. Please look at the rhythm. X minus x naught power 0 by 0 factorial. All of us know 0 factorial is 1. So f of x naught. Next, it starts with the first derivative, second derivative, and third derivative of f around x naught. And then accompanied with x minus x naught power 1 by 1 factorial, x minus x naught power 2 by 2 factorial. Double derivative is accompanied with power 2 and 2 factorial, x minus x naught power 3 by 3 factorial with the triple derivative and so on. Suppose if I have x is equal to, if I'm considering x naught is equal to 0, then I will have the expansion to be like this. Why I'm making a mention about this, there's a special name for this series, guys, that is Maclaurin series. This is called Maclaurin series. Again, this is proposed by Maclaurins. Okay. Yeah. Now, once you understand this rhythm or this rhythm of Taylor's expansion, I'll be extending the same rhythm to a function in more than one variable. That means what? Let f of x comma y be a continuous continuous function. Excuse me. With partial derivatives. Partial derivatives of, you all know, derivatives of f. Okay, you all know that when a function is in more than one variable, when f is in more than one variable, x, y, z, t, like that, then if I'm considering different derivative, then it would be partial. I cannot differentiate it completely. I'll be doing partially. So I'll be making a mention in the suffix, that is, I'm differentiating f with respect to x or y or z or t kind. Okay, so now, here I'm considering the function to be in two variables. Hence, I'll be writing the Taylor's expansion like this. Please have a look. It is just an extension. It will look something like this. What that is initially it is the function itself. Of course, I'll be considering about a point. Let f of x be a continuous function with partial derivatives of f. Now, the Taylor's expansion, the Taylor series expansion about point x naught y naught. If I say a point x naught y naught, then how am I going to write the is given by f of x naught y naught plus x minus x naught fx. Of course, there's one factorial here plus y minus y naught by 1 factorial fy. These are the first order derivatives. How does the second order derivatives look like? You all know the set of second order derivatives would be 4 in number. Okay. Of course, for the second order derivatives, I'll write it in the next line because I'll be having a second, 2 factorial. Okay. I'll be having things like this. X minus x naught whole square fxx double derivative. Then 2 into x minus x naught y minus y naught. Of course, if I take 2 inside, then this will vanish off fxy. And here you all know that fxy or fyx both are same, right? Plus y minus y naught whole squared fyy. This would be my second order derivative. Now, how will my third order derivative look like? Simple, guys. Always remember Pascal's triangle. What that is 1 to 1. The coefficient would be like the Pascal triangle. Okay. and then 1331, and then 1464 kind. Okay. So how will my third order derivative look like? I'll be having 3 factorial x minus x naught whole cube f triple x, third order derivative of f with respect to x, 3 into. Okay. Finally, see this one small logic. In every, for the second term or the 2 factorial term, the power of each term would be 2. I mean, derivative would be 2, power of each term. Here, if you see x minus x naught power 1, y minus y naught power. In total, it is 2. Again, here also, it is 2. Okay. So here also the same thing will follow. We all know a cube plus 3a squared b plus 3ab squared plus b cube would be the formula, right? X minus x naught whole squared, y minus y naught. You can see the power of this term is again 3. Okay. How will this be? Fxx, because x term is power 2 and y plus 3 x minus x naught 3ab squared. Okay. Y minus y naught whole squared. Okay, I'll just erase this Pascal triangle coefficients. All of you are aware of this Pascal triangle coefficients, right? Okay. Once you understand the logic, you will be able to write incessantly any number of derivatives. Now, y power has 2, so fx yy I will be considering plus y minus y naught whole cube f triple y means third 3 times derivative of f with respect to y plus and so on. Now, if you understand the logic, you will be able to write any number of terms in the Taylor's expansion. It's an infinite series expansion depending on the number of terms that we need for a problem we'll be considering. Okay. Usually for research problems, we'll be considering according to the accuracy of the answer that you are expecting. Yes. Now, once I'm done with the Taylor's expansion, next I immediately, without loss of generality, I'll be writing this expansion about x is equal to x naught. Let's see how it looks like. About I'm sorry, x naught is equal to 0 and y naught is equal to 0. How does it look like? By the way, it's again Maclaurin series. In the exam, you will be having either that or this. I shall tell you how the questions will come for your information. Okay, about x naught is equal to 0 and y naught is equal. Wherever x naught is there, I'll put 0. Wherever y naught is there, I'll be putting 0. Okay, so how will my expansion look like is, Taylor series expansion for f of x would look like this. F of 0 comma 0 plus, of course, 1 by 1 factor, I'll write it out. X fx plus y fy plus 1 by 2 factorial x squared, of course, just a second, I'll rewrite this again. Why? Because I am supposed to be putting the point 0 comma 0 as well, right? Okay. Fx at 0 comma 0 plus y into fy at 0 comma 0. When you are asked to write expand, you will be using this formula. When you are asked to write in the powers of x minus 1, x minus a and y minus b kind, then you'll be using the first formula. Okay. I hope I'm clear. I'll repeat it anyways in the problem. X squared fxx plus 2xy fxy plus y squared fyy. Okay. Yeah. Third one also I will write 1 by 3 factorial f triple x, of course, x cube accompanied with f triple x plus x 3x squared y f triple x at 0 comma 0, guys. Here also f double x at 0 comma 0, fxy at 0 comma 0, fyy at 0 comma 0. Okay. Now this one would be fxxy at 0 comma 0 plus 3xy squared fxyy at 0 comma 0 plus y cube f triple y at 0 comma 0. Okay. And things will go on and on like this. Okay. You can extend it for the fourth term as well, guys. This would be called Maclaurin series expansion. Okay. This would be called Maclaurin series expansion. I'll just make a mention of one small thing, that is when we are asked in the question, asked to find the expansion of f of x comma y in powers of x minus a and y minus b, or about the point A comma B, about the point A comma B, what I will do, I will use the first formula. We use 1. Okay. If in the question, if we are asked, just to expand, if we are asked to write Taylor's expansion, write Taylor's series expansion without giving any point or without mentioning about any powers, without giving a point or mentioning about powers, mentioning about powers of x and y, about powers of x and y, we go with second formula. We opt second formula. Okay, I'll write so that you have no confusion about what is 1 and what is 2. Okay, yeah. See, this is my first formula, guys. Okay, yeah. And this would be my second formula. This would be my second formula. Clear? Okay, yes. Yeah. Okay, with this, I will just end. I will do the next one. I mean, a problem on the next in the next video, please.